This 6551 UART chip provides an RS-232 serial interface to my breadboard 6502 computer. And this serial interface is going to make it possible to load and run much more complex interactive programs on this computer. Now, in a previous video, I showed you how this is all hooked up. We've got these 8 data lines here, those blue wires, hooking this chip to the data bus. That's here. And then we've got the chip select and register select lines hooked up to some address lines and some decode logic, which makes the 4 registers in this chip accessible at addresses 5000 through 5003. And those 4 registers are the status register, control register, command register, and then the data register, which if you read from it is going to give you the receiver data register. And if you write to it, it's going to put data in the transmit data register to transmit out. Previously, to communicate via RS-232, we were sending each bit individually here, and then using carefully designed delay loops down here to wait the right amount of time in between bits. So I'm going to delete all this because the UART is going to make all of this much simpler. So I'm just going to get rid of everything except for just the basic LCD routines. So we can still use the LCD. So we've got the initialization for that here. And we've got some of the subroutines down there for it. But otherwise, we'll get rid of all the serial stuff. And to use the UART, we're going to be using these 4 registers. So the data, status, command, and control at addresses 5000, 1, 2, and 3. So let's take a closer look at those registers. We'll start with the status register. So if we read from the status register, we're going to get a bunch of status bits that tell us various things. And for right now, what I want to do is get the 6551 and everything configured and working in kind of the simplest way possible. So I'm not going to be using all of these features to start with. For example, the interrupt bit, I'm not going to be using interrupts, but if I were, then this bit would tell us whether the 6551 had triggered an interrupt or not. Likewise with bit 5 and 6 here, DSR and DCD, data set ready, data carrier detect, I'm not going to be using those. Those would typically be used if we were using those pins on the RS-232 interface. We could feed those into the DCD and DSR pins of the 6551 and then read their status through the status register here. But we're not using those either. But what I am interested in is the transmit data register empty and receive data register full bits in the status register, because those are meant to give us important information about the status of sending and receiving data. So the transmitter data register empty bit, what that does is it tells us whether the transmit data register here is empty or not. And why would we care about that? Well, when we're transmitting data, the way that works is we write data to the data register, and when we write data to the register, it goes into the transmit data register here. And then it's going to be in that transmit data register, in which case this should tell us that the transmit data register is not empty, because we just put something there. And it'll be there until it's able to transmit it, because it's going to transmit it 1 bit at a time. That's going to take some amount of time to do. And then once it's done with that, what it ought to do is it ought to then set this to empty. And that tells us that that's now empty and that we're able to put the next byte into that register. So if we have a whole bunch of bytes to send, we would put 1 byte into that register, and then we'd read this status register to wait until the transmit data register is empty. And once it's empty, then we can put the next byte in, and it'll start transmitting that, in which case this will be not empty while it's transmitting. Once it's done transmitting, it should set that to empty, in which case we now know to send the next byte, put that in there, and so on. So if we have a bunch of bytes to send in a row, the purpose of this transmit data register empty bit is to tell us when to send each byte, because we're sending 1 byte at a time. Similarly, the receive data register full bit tells us when the external device that's connected to our serial port has sent us something. So if we've received something from that device, it'll go into the receiver data register, and the receive data register full bit gets set. So if we're expecting to receive data, we need to be monitoring that receive data register full bit, and whenever it's full, we then need to read from the data register to get that byte out of that register so that the next byte can be read. So in our case, what we're going to do is we're just going to be in a loop checking that receive data register full bit, and if it's ever set, then we read the data, and we say, we received a byte, let's read that. And as soon as we read it, then this gets reset to not full until the next byte gets received. Now, if we happen to receive a byte and then not read it in time, and then we receive another byte, that's called an overflow, or an overrun, in which case the overrun bit would get set. So if we're not reading fast enough from the receive data register and we got 2 bytes coming in, or multiple bytes coming in, there's no buffer here other than just that 1 byte. So it's just going to overwrite each one that comes in. But it will keep track that it did that. So we were able to detect that that error occurred and that we lost some data. And it does that by setting this overrun bit. And there's also a couple other errors that can occur. We can have a framing error where, if we're expecting a certain number of bits per byte and we don't receive that number, then it might detect that there's a framing error. Or if we've got parity enabled and there's a parity error, it can detect that as well. So we're able to detect if some of these errors have occurred. We may not be able to recover from it, but at least we can detect it. And so generally we're just reading from the status register. But if you write to the status register, that has a special meaning, which is to reset the 6551 chip. So we may want to do that at the beginning of our program here, right after the LCD initialization. And so what we do is just write some value to that status register. And I'll just use 0 because the actual value that we write is not all that important. It's just anytime you write anything to the status register, that's just a special signal to the chip to reset itself. So we don't necessarily need to do this, but I'm just kind of showing it to you anyway. Next, we've got the control register, which selects the baud rate and stop bits and word length and so on. And so here we can set the number of stop bits that we want. Normally we would just want one stop bit. So that's probably what I'm going to do, is set that bit to 0. Then we've got our word length, which is how many bits per word. We're just going to be using 8 bits. That's pretty common. So set bits 6 and 5 to zeros. And then we've got our baud rate. And so there's various different baud rates that are supported without having to do anything too complicated. We can just set this to whatever baud rate we want. And then we tell it that the receiver clock source is going to be that baud rate. So if I want to use the fastest baud rate, 19,200 bits per second, then I can just set all of these to 1s. And then, of course, we want our receiver clock to also be set to use that same baud rate. So we'll set that to 1s. So these are all 1s. So if we convert that to hex, we end up with 1F. And that's going to signify that we want 8 bits per word. We're not going to use any parity and one stop bit. And our baud rate's 19.2. And so then we'll store that in the control register. And it's as simple as that to configure the baud rate and everything the way we want. Then we've got the command register, and here is where we're setting our parity mode. So if we don't want to use parity, doesn't really matter what we set the parity mode to. We just set parity mode enabled to 0 to disable parity. So if we want no parity, we can just set all that to 0. This also has this echo mode, which is anytime you receive a byte, you can automatically echo that back. I'm not going to use that, so we'll just set that to 0 as well. And then, as I mentioned before, we're not going to be doing anything with interrupts. So I basically want to disable interrupts. So a couple of these options have interrupts disabled. This option here, 1-0, I think is what I want to use. So ready to send will be active low. Not that we're using that pin, but that's what it would be if we were in fact ready to send. And then we'll disable transmit interrupts. And then receiver interrupt request, we want that disabled as well. So we'll set that to 1. And then data terminal ready, again, we haven't hooked that up either. So that says data terminal ready. That's not hooked to anything. Ready to send, not hooked to anything. So it really doesn't matter too much how we set these, but I'm going to set that to ready because why not? And so all of that means that in hex, the command register is going to be 0B. And that pretty much has the effect of, saying that we don't want to use parity, we don't want echo, and we're not going to be using interrupts. And so I can go ahead and write that to the command register. And so that's everything you need to do in order to initialize this. And of course, if you want to use different options, different baud rate, whatever, you can use different values here. But, the simplest configuration, that's enough. That'll work. So now if we just want to start receiving data, we can basically just wait until the receive data register full bit gets set. And so to do that, we just want to read the status register and check to see if that bit is set and wait until it is. So let's do that. We can load the status register into the A register. And then to check if we've received any data, we can AND it with 08 hex. And what that's going to do is it's going to check to see if the receive data register full bit is set. That's bit 3 here, which is the 1, 2, 4, 8's place, right? So 08 is going to be, just that bit. So if we AND it with that, and that bit is set, then we're going to get 08. If we AND it with that bit and that bit is not set, so it's not full, then we're going to get 0, because it won't matter what these other bits are. So if we AND it with 08 to check the receive data register full and we get a 0, then we know that we haven't received anything yet, and we just want to stay in a loop. So we're anding it to check if the receive buffer status flag is telling us that the buffer's full. And if it's not, if we haven't received anything, then the result of that and is going to be 0. And we can use a branch equal, which is going to branch, if it's 0, back up and check the status flag again. So this will just sit in this loop as long as the receive buffer is empty. In other words, as long as we haven't received anything, we'll just keep sitting in this loop. Which means that as soon as we drop out of this loop, we will have received a character from the serial interface. So in that case, we'll have a byte in this receive data register, and we want to read it. So we can just read from the data register and put it into the A register. So if we load A from the data register, that'll get that byte that we just received. And then if we want, we can print that to the LCD. And I've already got a subroutine to do that, which is just the print char subroutine. And then once we print the character to the LCD, we can just jump right back up to receive wait and wait for the next character. And it's really as simple as that to receive data. So let's give this a try. I'll save it, assemble it, and write it to the EEPROM. Now if we stick this EEPROM back in and reset, we can pull up our terminal and give it a try. Of course, we need to change our baud rate, right? We selected 19.2 is how we configured it. 8 data bits, no parity, 1 stop bit, so that all looks right. And so here's our terminal. And if I try typing something, it should show up on the LCD. And look at that, seems to work. Of course, we're not receiving anything on the terminal here, and it's not echoing anything because, A, we didn't turn on echoing, and B, we haven't written any code to send anything here. So let's give that a try. Now, sending a character is very similar to receiving a character, so I'll just write a little subroutine here for sending a character. And if we call this subroutine with the character we want to send in the A register, it's really as simple as writing that character to the data register. And at this point, we could just return from the subroutine. But remember, when we write a character to the transmit data register, we are supposed to have to wait until the transmit data register empty indicates that it's empty. Otherwise, if we just call that subroutine again to write another character to the transmit data register, it's going to overwrite the character that we're trying to transmit, and it's not going to transmit properly. So to make this subroutine so that we can call it multiple times in a row to send multiple characters, we should have the subroutine wait until it's actually done transmitting before it returns. And to do that, we'll just check the status register. And just like when we were checking the receive buffer status flag, we can check the transmit buffer status flag by anding it with, in this case, 10 hex to check that bit. And so this bit should be 0 if the transmit buffer is still full. And so in that case, we want to just keep looping until it's not full anymore. And so what this will do is after we send the data, we're going to sit in this loop here, waiting until the UART tells us that it's done transmitting. And because we're loading something into the A register, the polite thing to do here is to push the A register onto the stack. And then when we're done mucking around with the A register, pull it back off the stack before returning from the subroutine. So this subroutine here should send a character, and there's a couple ways we can use it. One is just to echo what is being sent. So if we go up here to where we're receiving data, currently what we do is when we receive data, we print it to the LCD, but we could also send it back out the RS-232 to echo it. So that way when we're typing in our terminal program, instead of not seeing anything like we're currently doing, we'll actually see what we're typing in the terminal program. So that'll be nice. The other way we can use the send character subroutine is just to send other messages over the serial interface. So if we just have a null terminated string that we want to send, it should now be pretty straightforward to do that. So to send the message, I'll set the X register to 0 and use that to count which character we're on. Then load that character from the message, indexed by X, whatever that happens to be. If we load a 0, which means we've gotten to the end of our string, because this is a null terminated string, then we jump down to where we're done. So maybe that's going to be down here. Otherwise, we send the character we just read, increment X, and then jump up to send the next character in the message. And so that's a pretty straightforward loop that should send our message. So let's give this a try. Save, assemble, write to the EEPROM, get the EEPROM back in, reset. And now if I try typing something, you see it's echoing in the serial terminal as well as displaying on the LCD. But wait a minute, there's something that's not working here. So when we receive data here, we're printing it to the LCD as well as sending it back on the serial console. And sure enough, we see what we typed. This is what I typed. I typed testing. And so we see that on the LCD. We saw that echoing back here. So it's doing both of those things, the print char and the send char. But before it did any of this, it should have printed our message. And it never did that. So what the heck's going on there? Yeah, you can look through this code here. So we're loading X with 0. So we're going to start with message indexed, 0. So that's going to get the H. So we're going to load an H into the A register. And then we have a branch equal, which is going to say if that's a 0, then we go to done. But, H is not a 0. So we're going to fall through and do a send character. So it should print an H. That should be the first thing it does. But we don't see that. We just see it do nothing until I start typing. So it's like this code didn't even run. So it seems like something's not working right here. Well, if you didn't know better, you could spend a lot of time beating your head against the wall trying to figure out what's wrong with this. And that's because it turns out there's actually a hardware bug with this chip. The 6551 chip from Western Design Center, specifically, has a bug where bit 4 here, this transmitter data register empty bit in the status register, always says that it's empty. And so that means when we transmit something, we put it in this transmit data register, it's going to take some time to transmit. Well, as soon as we put that data there and we read the status register says it's empty, even though it's not. And that's a bug. It just always says it's empty. And so if we look at our code here, we go down to where we're sending a character. This whole process here where we're reading the status byte and checking the transmit buffer status flag in that byte and sitting in this loop, doesn't do anything. The first time as soon as we send the data and we read that status flag, it immediately says it's empty. And so we fall through this branch equal and we return from the subroutine. And so if we're sending this message where we're sending, one character after another without waiting, as soon as we send the H, or I should say, as soon as we put the H into the data register, it immediately says it's ready for the E. And so our program is going to come right back around here and put the E in there before it's actually done sending the H. And so it ends up corrupting that send. And ultimately, it doesn't send a valid character. And so nothing shows up in our terminal here. Now this works for when we're echoing because we're printing one character at a time. So as I'm typing here, after each character I type, I'm waiting long enough for it to be sent. But when we send this message, it's not waiting long enough because this status register is reporting the wrong data. And that's just a hardware bug. When I think it's great the Western Design Center is still producing these chips at all. In some sense, this is 40-year-old technology or more, but they're exceptionally educational. And so I'm glad that they're still being produced at all. But nevertheless, this chip does unfortunately have a bug. And I can demonstrate that by using one of the old original chips. So this is an AMI chip, 6551, the same sort of chip. And the date code on here says 8134, which suggests that this was manufactured the 34th week of 1981. So I pull out the Western Design Center one that has the hardware bug and put in this AMI one. I can demonstrate that there's actually nothing wrong with our code, that it truly is just a hardware bug. And there are a couple other subtle hardware differences with the new chip. For example, this old one, I had to ground the DCD pin to get this to work. But let's pull up the serial terminal again, and I'll clear the screen on that, and then reset the computer here. And you see it printed hello world right away. So this is obviously working quite a lot better. And then if I type into the serial terminal, you see that's working just the same as it was before. Both printing on the LCD and echoing back to the serial terminal. So you can see that a 6551 without a hardware bug works just fine. But unfortunately, these are getting harder and harder to find since the only ones they make anymore are the Western Design Center ones. And again, I'm glad they make these. But yeah, unfortunately, they do have the bug. So how can we work around that? So how are you supposed to figure out that there's actually a bug with the hardware? Because you could really beat your head against the wall for quite a while trying to get this to work. Well, there's nothing in the datasheet that says that. Even if you go to the back, there's a section here on errata that says, there are some known issues with this. But, if you read through this, it's not the issue that we're encountering here. This is talking about something different. However, if you look at this datasheet, this is from 2007. Turns out there's a newer version of this datasheet from 2021. And if we go look at the section here on the status register in the latest version of the datasheet, you can see they've actually changed this. So it says for a transmitter data register empty, you can see a 1 indicates that it's empty, and a 0, it's never 0, is what it says. So it actually kind of, documents the bug So maybe it's not technically a bug. It is documented. And there's an asterisk there that says, that the transmit data register and transmit shift register are loaded at the same time. And so a delay should be used to ensure that the shift register is empty before the transmit data register is reloaded. So they're telling you to use a delay before reloading the transmit data register rather than trying to read this bit 4 because, as the datasheet now says, bit 4 is never 0 during transmission. Well, the problem is that after we send a character, we check the status register and it immediately says that the transmit buffer is empty. And the problem is that it's not empty because there's some serialization delay that it takes to send each bit of that byte out. And one workaround that we can use is to add a delay here that just waits for, the amount of time that it takes to transmit that entire byte. And basically this delay subroutine is just going to create a loop that loops for a period of time. And so I'll use the X register to count how many times through the loop. And we'll initialize that as 100. And then each time through the loop, we'll just decrement X. And if X has not gotten to 0 yet, then we'll branch back up to the top of the loop. And we need another identifier here to branch to because we don't want to reinitialize X again. We just want to decrement it and then keep looping. And then once X gets to 0, it'll drop out of this loop and we can return from the subroutine. But of course, we don't want to mess up the X register, so we should push X onto the stack at the beginning and pull it off the stack at the end. And so that'll create a delay that's long enough to empty out that transmit register. But the question is, how do I know that this delay is going to be long enough? Where did I come up with, 100 times through the loop? How do I know that's going to be enough? Or how do I know that's not going to be too much and it's going to slow down the serial communication? Well, it's going to be based on the baud rate. So if we're sending 19,200 bits per second, then if we take 1 divided by 19,200, that tells us how many seconds each bit's going to take. And what we want to know is how many clock cycles in the processor it's going to take. And our processor is running at 1 megahertz. So if we multiply this by 1 million clock cycles per second, that tells us that 19,200 bits per second is 1 bit every 52 clock cycles, if our clock is running at 1 megahertz. But we don't want this delay to be 1 bit time. We actually want it to be the entire byte. And so the byte is going to be 8 bits, but there's also a start bit and a stop bit. So really, it's going to be 10 bit times. So if we multiply this by 10, we really need this delay to last for 520 clock cycles. And it turns out that with X initialized to 100 here, that's about what it does, because this decrement X takes 2 clock cycles, so that's going to be 200 clock cycles there. And the branch not equal, if the branch is taken, is going to be 3 clock cycles, so that's 300 there. So 200 plus 300, there's 500 clock cycles right there just in that loop. And you get another, close to 20 if you consider that the jump to the subroutine is going to take 6 clock cycles. Pushing X onto the stack is another 3, loading X is another 2, pulling X is another 4 clock cycles, and returning from the subroutine is another 6 clock cycles. So we get pretty close to that goal of 520 clock cycles. So by adding this delay in here, let's save that and write that to our EEPROM and give that a try. So I've reprogrammed the EEPROM, got the EEPROM back there. I've swapped back to the Western Design Center chip and reconfigured this so it's just the way it was before. And so I'll bring up our terminal and clear the screen on that and then reset the computer. And it looks like maybe I tapped the reset twice. We got 2 hello worlds. That's no problem. I guess I could try again just to demonstrate that it really is working. So reset. There we go. I still think I double tapped. Anyway, when it resets, it's printing hello world. Okay, I'm going to do this right. There we go. So it prints hello world when it resets. And then if we type something into the terminal, that works as well. So it's not ideal that we've got that hardware bug, but it is something that we can fortunately work around in software. And even though we're back to using a delay loop, which is kind of what we're trying to get away from with the UART, it's still much simpler than having to bit bang individual bits to transmit and receive serial data. But I think this really sets us up well to run some interesting interactive programs on the computer now that we have an easy way to transmit and receive data across the serial interface like that. And so that's what I'm going to do in the next couple of videos on this is get some more interesting software running on this computer. But in the meantime, remember, if you want to build your own 6502 breadboard computer like this, I sell kits for everything you see here on my website, eater.net/6502. Check that out for more. I've got schematics, everything else you might want there. And as always, thanks to all my patrons who help make these videos possible.